Hello everyone, I am Kritika Tank from 5th semester CSC. Today I am going to be presenting on the topic Deterministic Finite Automata. In the theory of computation, a branch of theoretical computer science, a deterministic finite automata DFA, also known as deterministic finite acceptor, a deterministic finite state machine DFSM, a deterministic finite state automation is a finite state machine that accepts or rejects a given string of symbols by running through a state sequence uniquely determined by a string. DFA refers to deterministic finite automata. Deterministic refers to the uniqueness of the computation. The finite automata are called deterministic finite automata if the machine is read and output string one symbol at a time. In DFA, there is only one path for specific input from the current state to the next input state. DFA does not accept the null bool. That is, the DFA cannot change the state without any input character. DFA cannot contain multiple final state. That is, it uses in the lexical analysis in the compiler. Now we will look at a formal definition of a DFA. A DFA is a collection of 5 tuples. We define DFA as A is equals to Q, sigma, Q naught, F, delta, where capital Q is finite set of states, sigma is finite set of input symbol, Q naught is in initial state, capital F is final state, delta is our transition function. The graphical representation of DFA can be done as following. A DFA can be represented by diagram called state diagram, in which the state is represented by vertices. The arc labeled with an input character shows the transitions. The initial state is marked with an arrow. The final state is denoted by a double circle. Applications of deterministic finite automata. Deterministic finite automata, also known as DFA, is a mathematical model that is widely used in computer science and other fields for recognizing patterns in strings. The main advantage of DFA is that it is easy to understand and implement, as the transition function is fully defined and the automation's behavior is completely determined by its current state. Due to this property, DFA has been widely used in various applications such as language recognition. One of the most common application of DFA is the recognition of formal languages. DFA can be designed to recognize a specific language, such as programming language or a markup language, by specifying the set of acceptable strings in the language. Second application of deterministic finite automata can be text processing. DFAs are used in text processing applications such as spell checkers and text editors to recognize patterns in text and perform specific actions based on those patterns. Next application is network protocols. DFAs are used in the design of network protocols such as TCP/IP to specify the sequence of events that must occur during communication between the two devices. Fourth application is lexical analyzing. DFAs are used in lexical analysis, which is the process of breaking down a stream of text into individual words, phrases, and other elements. Deterministic finite automata plays a major role in other applications such as cybersecurity, where DFAs are used in cybersecurity to detect and prevent malicious activities by recognizing patterns in network traffic. Pattern matching. DFAs can also be used to match regular expressions in text, which is a common task in text processing and data mining. Other applications include automata testing. DFAs are also used in automatic testing to check for specific input sequence and respond accordingly. Formal verification. DFAs can be used in formal verification, which is the process of mathematically providing the correctness of a system or algorithm. In conclusion, deterministic finite automata (DFA) is a mathematical model that is widely used in computer science and other fields for recognizing patterns in strings. Now we will look at few problems on deterministic finite automata. Problem number 1. Construct a DFA for a set of strings over a, b such that the length of the string is 2. The explanation is as follows. The desired length of the language will be as AA, AB, BA, BB. The state diagram of the language will look like this. Here, state A represents set of all strings of length 0, state B represents set of all strings of length 1, state C represents string of all strings of length 2. State C is the final state and D is the dead state, so it is because after getting any alphabet as input, it will not go into the final state ever. The number of states needed are n plus 2, where n is the length of the string. Above automata will accept all strings having the length of the string exactly 2. When length of the string is 1, it will go from state A to B. When the length of string is 2, it will go from state B to C. When the length of string is greater than 2, it will go from state C to D, and D is the dead state. After it goes to D, then from D it will go to D itself. Looking at the second problem, which says construct a DFA for the set of strings over a, b such that length of the string is greater than equal to 2. That is, length of the string should at least be 2. The desired language will look like L is equals to AA, AB, BA, BB, AAA, AB, AAB, ABA, ABB. The state diagram of the language will look something like this. Here, state A represents set of all strings of length 0, state B represents set of all strings of length 1, and state C represents set of all strings of length 2. Number of state n plus 1. Here n is of length of string greater than equal to n. The above automata will accept all strings having of length string at least 2. When length of the string is 1, then it will go from state A to B. When length of the string is 2, then it will go from state B to C. Lastly, when length of the string is greater than 2, then it will go from state C to C itself. Lastly, we are looking at the problem number 3, where we are constructing of a minimal DFA accepting a set of strings over a, b in which number of AW mod 2 is equals to 0. That is, number of mod 2 is equals to 0. Number of A should be divisible by 2, or number of B should be divisible by 2, or both by divisible by 2, where W is number of strings over A, B. The desired language will look like L1 is equals to null string, AA, or AABB, AAB, BB, BBA. Now, next we will look at the transition diagram. The state transition diagram for the desired language will be looking like below. Here we can see that each string of the above language are satisfying the condition of the given problem. Here, null string is accepted because the number of A and B are both are 0, and rest of the string having A divisible by 2 or B are divisible by 2 or both are divisible by 2. But below language is not accepted by DFA because its strings are not satisfying the condition of the given problem. Here we can see that none of the string of above language is satisfying the given problem of the above string. In the above DFA, in each state there is a state name A. Just above it there is EE, which indicates the number of A is even and number of B is even too. For name B, just above it there is EO, which indicates number of A is even, number of B is odd, and so on. Initial and final state A. On getting A, the input it transitions to final state B. On getting B as input, it transitions to another final state B. The final state B on getting A as input it transitions to state C. On getting B as input, return back to initial state A. The another final state D, on getting B as the input, it transitions to state C. On getting A as input, it returns back to initial state A. The state C, on getting B as input, it transitions to final state B. On getting A as the input, it returns back to the state B. Now let's look at a few key points. DFA stands for Deterministic Finite Automata. For each symbolic representation of alphabet, there is only one state transition in DFA. DFA cannot use an empty string transition. DFA can be understood as one machine. In DFA, the next possible state is distinctly set. DFA is more difficult to construct. DFA rejects the string in case it terminates in state that is different from the accepting state. Time needed for executing an input string is less. All DFAs are NFAs. DFA requires more space. Dead configuration is not allowed. Example, if we give input as 0 on Q0 state, so we must give 1 as an input to Q0 as self loop. Backtracking is allowed in DFA. Conversion of regular expression to DFA is difficult. Epsilon move is not allowed in DFA. DFA allows only one move for single input alphabet. Thank you.